So today is a very important day because we're going to describe Noether's theorem for fields, for classical fields, or Noether's theorem for continuous systems, the way you want. Okay, so let's start with this. Noether's theorem for classical field theory. And essentially, even though we will not discuss this at all, essentially this theorem is exactly what you will find also in quantum field theory. So in quantum field theory is exactly the same statement, except that instead of talking about classical functions, classical fields, you'll be talking about operators, okay? But it's the same thing. So learning this, you're learning a lot. And also, as you will see, it generalizes what we saw, about Noether's theorem for a system with a finite number of degrees of freedom, where we were not doing field theory. So this is an interesting result. Before we get into this, since we're going to make transformations, we're going to make transformations of fields and variables. Let's make clear what we understand by a transformation. Okay, so we will start with an example so that we understand each other, what we understand, what we mean by a transformation. So let's think of a rotation R of a vector in 3 dimensions. Okay, so that's the simple case. All right, so what do we mean by a rotation? We mean that we change x into x prime, and this x prime is a rotation operator, or essentially a rotation matrix acting on x. Okay, so that's what we mean. Yes, and also if we say this, we are also saying that x is r minus 1 times x prime, right? So the minute we say how x transform, we also say how x and x prime are related, okay? In practice, we will use that the transformation, in this case the rotation, is going to be close to the identity. So we will take that, the transformation is 1 plus a very small object, a very small parameter. So this delta r will be much smaller than 1. But this is not essential for the thing that I'm discussing here, but I just want to say it so that you will see that that's exactly what we will do later on. So then if a vector transforms like this, and this is what we mean by putting an arrow on top of the symbol, then any vector transforms like this. So it also goes like b goes to b prime equals rv, okay, where v is a constant. Okay? Now, if we have a function phi of x, okay, this function, how do we transform it? Well, phi does not transform because it doesn't have an arrow on top, so it's not a vector, but x is a vector, so we have to transform x. So that means that this goes to phi of x, which is r minus 1 of x prime. That is the transformation. We transform x, but x is r minus 1 of x prime, so that's what it is. And of course, what we are saying is that phi of r of minus 1 of x prime, since this is x, this is also phi of x. Okay? So we only transform x, we don't transform phi. Now, after we transform x into x prime, because of this r minus 1 is not the identity, is close to the identity, but not the identity, then the functional dependence of this object on x prime is not the same as the functional dependence of phi on x. So the function has changed, right? So this function now is different, as a function of x prime relative to what it was as a function of x. So this is how a function phi of x transforms. And we say phi of x is a scalar. Okay, so that's how a function, a scalar function, transforms. Now, we have to combine the two things now. So imagine that now we have a vector function, v, okay? We have a vector function b, which depends on x. So we're going to have the composition of the two things. V itself is going to change because V is a vector, has an arrow on top. And then the dependence on X is also going to change, as in the case of the scalar function. So the two things together means that this transforms into R times V, function of X. And now we transform X. So this is R times V, and X is R minus 1 of X prime. Okay? And now, again, the dependence on X prime is not the same as the dependence on X because there is this R in the middle, okay? So that means that this is nothing but, a new dependence. We call it B prime on the new variable X prime. So that's how we transform things, okay? So is this clear? Because this has to be crystal clear before we start, discussing Noether's theorem.
Yes, it is clear.
Okay. So V is a vector function, right? All right, so now let us close this parenthesis. All right, so this was a parenthesis. And now we're gonna, start, the actual Noether's theorem. Now, for Noether's theorem, we're going to group together T and X, and we're gonna call this thing X mu. Okay, so T and X, we're gonna put it together into some column, okay? And this we will call X mu. This X mu, of course, in relativity, it's clear what it is, right? But I mean, that doesn't mean that we're going to be discussing only relativistic theories. If the theory is not relativistic, this is going to be just a notation, just a shorthand for writing, instead of T and X separately, we're just going to put it together, okay? So that means that this object here is not necessarily to be considered a Minkowski for vector. Minkowski for vector. What I mean by this is, again, I repeat, okay? Let me emphasize this thing. I mean, if the theory is non-relativistic, this is just a notation. I just put them together, not to have to write too much, okay? If the theory is relativistic, then of course, this is going to transform under Lorentz transformations in a certain way. But if the theory is not relativistic, there is no Lorentz transformations to talk about, okay? And this is just a way of writing, a little less, okay? Now, so now we're going to talk about transformations. So let T be a transformation of the form, and this means that we're only going to consider continuous, and infinitesimal, infinitesimal. Which means that delta of everything is going to be much smaller than 1, okay? So the transformation T is going to be 1 like this. So X mu is going to transform under T into X mu prime, which is going to be the old X mu, so close to the identity, plus a little bit. And this little bit is going to be much smaller than 1, but in general, it's going to be X dependent itself, okay? So that's a transformation for X. And when we transform X, in general, we are also going to transform the field eta of X mu. So under T, it also changes into eta prime of X prime mu. Remember what we did with the vector function, okay? And this is going to be eta of X mu plus delta eta of X mu. Okay, so let's pause here a little second here and think about what we have written. You know, let's go back. Okay, so here you see that V of X goes to R V of X. So before I change X into X prime, the transformation is just a transformation of the field V itself, not of the variable. Okay, so this is exactly what we are doing here. So this transformation here, this variation with respect to the identity, is only the variation of eta itself. Okay, it's not the full transformation, because the full transformation now would require that I write X as a function of X prime. The full transformation would require that now I write X as a function of X prime. And this I haven't done. Okay, this I have not done. So that means that this transformation, this extra piece that I add here, measures the transformation of eta itself, okay? And not of X. All right, so that's what this means, and it's done like this. So here this delta eta measures only the transformation of the field eta, not of the variable, because in this way, you know, Noether's theorem is written in a simple, in a more simple way. So that's why this thing is done. Okay, so that means, for instance, if eta of X is a scalar, then delta eta of X is how much? Who can say this? Let's imagine that eta of X, the transformation T is such that eta of X is, under this transformation, a scalar function, is a scalar. So then how much is that delta eta?
Zero.
Exactly. Very good. Yes, it's 0. Okay? Now, in general, we are not going to have just one field. This would be nice, but I mean, things are usually a little bit more complicated than that. So we can have more than one field, okay? So if we have more than one field, then that means that we're going to put all the fields together. And so this is going to be eta 1, eta 2, eta n, if we have n fields. So rho is going to go from 1 to n. So that means that this collection of fields, I'm going to group together again with an index row. So this is going to be an index row, and this is going to be an index row. So that means this index row here is just, you know, to collect all the fields together into one single object. If this index row is a Lorentz index, then eta is not a scalar, transforms under Lorentz transformations. But that depends, right? I mean, the index row is just a way to group together, to label, okay, all the fields into one single object. All right? Now, so this is just regarding the transformations, okay? So this is how we are going to transform the objects that we have in our Lagrangian. But this is just a general transformation. It's still not a symmetry transformation, okay? So, in general, let us see what a transformation does to the Lagrangian, right? So in general, one finds that under a transformation, the Lagrangian density transforms and is not the same. It goes from an L to a certain L prime with L different from L prime. And also, the action is different before and after the transformation, right? The action is also different before and after the transformation, where I is the action of the system. By the way, for reasons that I don't know, it becomes quite often the case that, the action in classical field theory is called I instead of S, right? Up until now, the action for, for the discrete system was called S, sometimes A, but most of the time S. Now, I mean, many places, they call it I, the action of the system. So I'm going to use that notation so that you guys get to see all the possibilities. Okay, so this I is going to be now the action of the system. Okay, so yeah, so we make a transformation and things change. So there's nothing special about that. Now, since eta of x transforms under T into a new field, which is a function of the old field, okay? And if it has an index, it has an index, okay? So rho, if this is a collection of these fields. Well, that means that the new action, which is a function of the new field, is through this dependence also a function of the old field, right? Because the new field is a function of the old field. And so the action as a function of the old field, this dependence is different from this dependence. In general, that's what is going to happen in general, right? So what we are saying is that when we change variables, of course, the functional dependence, in terms of the new variables, is not going to be the same as the functional dependence in terms of the old variables. The functional is going to change, okay? So that's what happens in general. Now, definition. T is a symmetry transformation so it's not any transformation, but a symmetry transformation when the dependence of the new action on the new field is the same before and after. Okay, so this dependence on the new field is exactly the same as it was before any change. So the functional dependence is the same. Okay, so that means because the functional dependence is the same, that means that the action the action I retains the same form. And that guarantees that the equations of motion, the equations of motion retain the same form. Under this symmetry transformation T. Okay, so let us see what this means. Okay, so that means that if T is a symmetry, then what has to happen is that I of eta prime, which is I prime of eta prime, but I prime of eta prime is I of eta. So that means this is the same. This is going to be the condition, right? So we demand for a symmetry transformation that the action does not change form when I change all these variables. Okay, and then that means linking this with this, that means that the action in terms of the new fields is the same as the action in terms of the old fields. Okay, so that is the condition we're going to impose. Any questions so far?
No.
Okay, so let us write down now what the action is, right? So since the action in terms of the old fields and maybe also derivatives of the old fields is by definition integral d for x over a four-dimensional volume. That means integration. This is just a quick way of writing integral over t, integral d3x. Okay, so I just write it like this. And this is the Lagrangian density, which is a function of the fields, also derivatives of the fields. And I'm going to accept, to be as general as possible, that this Lagrangian density also depends explicitly on x. So, I mean, obviously, these guys also depend on x. Remember that x now is x and t, both. So I'm going to accept that, the Lagrangian density also depends on x. If it doesn't, then the situation is going to be a little simpler. But if it does, then I'm going to keep it, okay? So that's the old action. Now, the new action, of course, depends on the new fields and derivatives of the new fields. And this is going to be the integral over x prime, the new volume, because x also has transformed. And this is a new Lagrangian of the new fields, of course. And derivatives of the new fields and the new variables x, okay? And what we demand is for a symmetry transformation, is that I of the new fields is I of eta. Okay, so let's write this whole thing. Why can't I go back? I don't understand why you cannot go back. I'm having a little technical problem here. Oh, damn, but what is going on? I want to go back. I'm sorry, guys. I'm having a problem here. I cannot, go back and forth for some reason. Why is this so? So this I can do. This I cannot do. Oh, man.
And you close it and reopen.
See, I'm gonna try that. Yes, I'm gonna do it. Let's see what happens. Okay, that worked. Okay, that was a good idea. Thanks. Yes. I don't know what happened. The first time that I have this stupid problem. Anyway, so that's the action of the system. This is the condition, right? And this page disappeared. Here it is. 18, 19. Okay, so this asymmetry. Yeah, but this page disappeared. That's interesting. This page disappeared. Okay, well, let's write it again. Well, since the action is a function of, this is the all fields, is by definition integral d4x of b4. The Lagrangian, so this is again the same thing. Okay, this of course depends on x in principle, x. And the new action depends on the new fields and derivatives. So that's b4 prime, d4 x prime, and this is a new Lagrangian density of the new fields. Okay. And this has to be, so let me just go back. So I of theta prime has to be I of theta, and also I of theta prime, I prime of theta prime has to be I of theta prime. So that means that this has to be I of theta prime. So this is the condition that we're imposing. Okay? So now, the condition I of theta prime equals I of theta. So that's this condition here. I of theta prime is I of theta. So after I change fields, the action is the same, leads to some form for the new Lagrangian. So the new Lagrangian as a function of the old fields okay, if I want the action to be the same, so one condition is that the Lagrangian should be the same, right? So that's the obvious one. But we have already seen that we can add something to the Lagrangian without changing the action. Or we can add something to the Lagrangian without changing the equations of motion. What is it that we can add here? Who can tell me?
A derivative of a function with respect to x mu.
Exactly. So a derivative of a function with respect to x mu or x nu. Yes. So that's this thing. Okay. So this is what we can add where this object here is the derivative with respect to time or the derivative with respect to space. Okay. The two things. So that means that T is a symmetry if and only if, because this is a definition, the difference between these two things is 0. So 0 has to be the integral d4x prime over b4 prime of L prime, which is L of eta prime rho comma nu x prime, plus this derivative of an arbitrary function, minus the integral d4x of the old Lagrangian. Eta rho comma nu, and x. So this has to be 0. So that's the condition we will have to work out now and see, you know, what it gives us. Okay, and, is that clear up to now?
Yes.
Yes.
Okay, so notice that because we are considering this function, which depends on the fields and explicitly on space and time, this derivative has to be total derivative and not partial. So this, I'm just making explicit what we have already discussed several times. So this d dx of omega of eta and x, okay? So that means d dx of eta of omega, which depends on eta of x and x. So that means that this is the derivative of omega with respect to eta times the derivative of eta with respect to x plus the derivative of omega with respect to x explicitly, right? So that's the chain rule. And if I have several fields, then I sum over all the fields. If I have several x's, I sum over all the x's, right? So this is, but that's the chain rule. If this x were not here, this partial derivative would not be here, okay? Furthermore, same thing happens for the equations of motion. When the Lagrangian depends on x explicitly, then the equations, the Euler-Lagrange equations, let me just write it down explicitly. The Euler-Lagrange equations become derivative with respect to x mu, total derivative of the partial of L with respect to eta comma mu equals derivative of L with respect to eta, right? And so this derivative takes the derivative with respect to x of the whole thing. And if L has an explicit time or explicit x dependence, time or x dependence, then this derivative also takes the derivative of that. And then it becomes partial, huh? Okay? Now, so we, keeping this in mind, we saw that the symmetry transformation leads to this condition, So this 0 is the integral d for x prime over b for prime of the Lagrangian of eta prime rho, which depends on x prime, eta prime rho comma mu, which depends on x prime and x prime, minus the integral over v4. Let me just put the other object here. I'm going to put it here. Plus d mu omega omega mu of eta and x. Okay, omega tan x minus integral over b4 d for x of the Lagrangian of eta of rho, eta rho comma mu of x and x. So that's the condition that we have. Now, first thing that we can notice is that this new function, omega mu of eta and x, okay, this new function appears because we have done a transformation. right? If we had not done a transformation, there would be no extra piece. Nothing would change, and in particular, this guy would not be there. So this guy is there only because we have made a transformation. And what it does, it changes L by a little bit. So that means that this new term here is of order delta, and therefore much smaller than 1. Remember that we are making a transformation close to the identity. And therefore, it does not matter which variables whether they are primed or unprimed, we choose for it, right? So that means that here I can put primes or not. So I simplify my life by not putting primes, because this object is itself of order delta. So the difference between primes and unprimed is also of order delta. So keeping that difference would be of order delta squared, okay, which I don't want. So that means that I can, with impunity, as it says, right? With impunity, I can just, suppress all the prime variables. Okay, is this also clear? This is something that we also did in the case of a system with finite degrees of freedom, with a discrete system. So it's the same argument. Okay?
Okay.
Okay.
Now we're going to transform the Jacobian. That's the first thing we're going to transform. Okay, so because we are changing lots of things, so we have to go step by step. Now, d for x prime is, as any Jacobian, d for x times the Jacobian determinant of the prime variables with respect to the unprime variables. Okay, with, remember, prime variable equals unprime variable plus a little bit. So that's the transformation that we made, okay? And remember that delta x mu is much smaller than 1. Okay, so let's compute this Jacobian. And it's actually much easier than it will look like, because we are only interested in terms of order epsilon. So let's look at this Jacobian determinant. So this is the determinant, as all Jacobians, of the derivative of the prime variables with respect to the unprime variables. And this is a matrix with two indices, right? So let's, let's write here what this determinant is going to look like. It's going to be a determinant 4 by 4, right? Because the mu index goes 0, 1, 2, 3. So that's 4 of them. And now, in the diagonal, we're going to have the derivative of x prime 0 with respect to x0, x prime 1 with respect to x1, and 2 with respect to 2, 3 with respect to 3. But for instance, let's take the 0 one, x prime 0 with respect to x0. X prime 0 with respect to x0 start with a 1 because of this guy. And then it comes with an epsilon term, right? So that's going to write here an order epsilon term. The order epsilon terms comes from the derivative of this with respect to x or x prime, right? So this is the order epsilon. But if I take the derivative of x prime 0 with respect to x1, which would be the first guy here, then the 1 is not there. Take x prime 0 with respect to x1, okay? This guy is not there, and it starts with an order epsilon. So the other guys are order epsilon, and the next guy is also order epsilon. 1, 0, 1, 2, and 3, an order epsilon. All these guys are order epsilon. Okay, here is also order epsilon. In the diagonal, it's again order epsilon, has a 1, because now I'm taking the derivative of x prime 1 respect to x1. But here is again order epsilon and order epsilon, and the same thing here, epsilon, epsilon, epsilon 1 plus order epsilon. This is epsilon, 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 1 plus order epsilon. So that's the structure of this matrix, okay? And I have to compute the determinant of this thing. So this determinant is gonna look, you know, a lot simple, okay? Very simple. Why? Because if I only want terms of order epsilon, I definitely have, you know, for this determinant, the product of these 4 terms in the diagonal that I have. 1 plus the sum of all the order epsilon terms in the diagonal. That I have. But the minute I take another element of the matrix to compute the determinant is of order epsilon square. So all the others are order epsilon square. So this is order epsilon, order epsilon, order epsilon, order epsilon, order epsilon, and order epsilon. So that means that the determinant to order epsilon is actually very simple. Is this 1 plus the sum of the epsilon terms in the diagonal, but that is the same as the derivative of x mu with respect to x mu. So x0 with x0, x1 with x1, x2 with x2, and x3 with x3, plus order epsilon squared. So it's as simple as this. Okay? Now, questions. Do we agree on this?
Yes.
Okay, no questions or comments? Okay, well, then we already transform one term, the Jacobian. So that's 0 equals integral d for x b4. And here it comes this term that we just computed. So it's the derivative of delta x mu with respect to x mu. And then it comes the Lagrangian, eta prime function of x prime, eta prime derivative with respect to x prime and also x prime, minus L of eta derivatives of the field and plus d mu omega mu. This term is also there. Okay, now the rest of the proof of Noether's theorem is going to be an exercise in index and index relabeling and what people call index gymnastics, right? So now we have to be careful and write things clearly. Okay, so now we start, you know, transforming the eta prime fields in terms of the eta fields and start expanding. We have to expand this term here. Of course, there's going to be a cancellation at a lowest order between this guy and this guy with a 1. But so we have to do it, you know, carefully and slowly. So this is the Lagrangian, which depends on the everything primed. And now, because we are transforming eta prime rho of x prime as eta rho of x plus delta eta rho of x, of course, this is going to be the Lagrangian of eta rho of x plus delta eta rho of x. And then it's going to be eta rho comma alpha of x plus delta eta rho comma alpha of x. And then x plus delta x. And this, of course, is going to be the Lagrangian itself. So Lagrangian of eta rho of x, eta rho comma alpha of x and x, plus something else. And this something else is going to collect all the terms that come from, delta eta rho, comma alpha, and delta x, everything else, okay? So this delta L, of course, is the derivative of L with respect to eta rho, delta eta rho. So that's due to the change in eta rho. The derivative of L with respect to eta rho, comma alpha, and then the variation of delta eta rho, comma alpha. And finally, the derivative of L with respect to x mu, delta x mu. And now we have to compute each of these terms. And the first term that we want to compute is this guy, because this we know from the transformation, but this we have to work out. Huh? So now, let's work out this guy. Okay, how do we compute this thing? Well, who is eta prime rho, comma alpha of x prime? By definition, is the derivative with respect to x prime alpha, the variables of eta prime rho of x prime, right? So that's the definition. If we had not changed x and x prime, it would be much easier. But since x and x prime also change, okay, so we have to be more careful. So that means that this is the derivative with respect to x prime alpha. Then we have eta rho of x plus delta eta rho of x. So that is the transformation of the eta prime. So remember that the eta prime, this delta eta rho, okay, takes into account only the transformation of the eta field and not of the variable x prime. So that's exactly what we did. So this is the transformation of eta prime of x prime as we define it. So let's go back and make sure that this is exactly what we did. Because now it will make a difference. Exactly. So you see, right? So x prime on the left, x on the right, and this is delta eta. So, okay. So this is delta eta, exactly how we defined it. Okay, so this is the same as the derivative with respect to x prime alpha of eta rho of x plus the derivative with respect to x prime alpha of delta eta rho of x. Explicitly, yeah? I'm going very slow. Okay, so now this I have to change because I have to take the derivative with respect to x prime of eta of x. So that means that this is going to be the derivative of eta rho of x with respect to x beta times derivative of x beta with respect to x prime alpha. That's the chain rule. That's the chain rule because the dependence on x prime is through the fact that, x depends on x prime. So that's the chain rule. And that's the derivative of this first guy. Now, the second guy is much easier because since this delta is already of order delta, right? It's of order epsilon, much smaller than 1. Here, keeping the difference between x and x prime is of second order. So this is already the derivative with respect to x alpha of delta eta rho of x. So here I can just, forget about the prime dependence. Okay, now I have this, okay? Remember that the transformation as we defined it was x prime mu equals x mu plus delta x mu, which depends on x. So here I have the derivative the other way around. So it's the inverse, right? So that means that I have to write, x as a function of x prime and take derivatives. So that is this object here is delta beta alpha, which is, the first guy, minus, because I'm inverting, it's the opposite. It's not x prime with respect to x, but x with respect to x prime. So that's where this minus sign comes from. Derivative of delta x beta with respect to x alpha. And then the derivative of eta rho x with respect to x beta plus this object here, which I'm going to write as d alpha delta eta rho of x. Okay, so any questions or comments? If anyone is lost here in this, do I have to do it more explicitly, or everybody will be able to reproduce this? Is this clear, or anybody's already lost? We need to go, with a few more steps in between. Is it clear or not?
Yes, all clear.
Okay. All right. So let's collect all the pieces, right? So the delta term with this guy, fixes this beta to be alpha. So this is the derivative alpha. Let me just make it explicit. I mean, soon I will have to write a little less, because otherwise the formulas are going to be very long. Huh? But so this first term is going to be derivative of eta rho of x with respect to x alpha. That's the first term. And then there are two terms. One of them is the derivative of eta rho with respect to x beta of x times the derivative of delta x beta with respect to x alpha. So these are these two, this times this with a minus sign, plus derivative alpha of delta eta rho of x. So this is what is going to give us this variation, right? Because it says that all the prime variables equal, the unprime variables plus something. So this something, these two terms, are the variation of eta rho comma alpha that I'm looking for. So this is this variation that I'm looking for. Okay. So now this I'm going to use in here, and this I'm going to use in here, and I'm going to plug it into this to compute this zero in a very complicated way, as you guys are saying. Okay. So now remember the form of this. Now I'm going to write that zero as an integral d4x over b4 of 1 plus the derivative of delta x mu with respect to x mu. That comes from the Jacobian. Now I have, the Lagrangian plus variation of the Lagrangian minus the Lagrangian plus d mu omega mu depends on eta and x. So all these terms. And I'll be more explicit in a second, but this is just so that you see that this for d4x over b4, the one with the L gives me an L, the one with the delta L gives me a delta L, then there is the L with the extra term in the Jacobian, then minus L, okay, and plus d mu omega mu of eta and x. So as you can see, the lowest order term cancels out, as it had to happen, okay? And so we have that 0 has to be the integral d4x over b4 of L times this term first, for instance, derivative of delta x mu with respect to x mu, plus we're going to write now the omega term here, okay, and plus delta L. And this delta L is now this collection of three terms. So these we have to write it explicitly now. So this is going to be dl eta rho delta eta rho plus dl d eta rho comma alpha delta of eta rho comma alpha, well, we just computed in the previous slide, and dl with respect to x mu delta x mu. Okay, so this is what we find. And so this whole thing has to be 0 for T to be a symmetry transformation. So this is now this whole thing now is, oh, sorry, is the symmetry test. Remember, we had a symmetry test in the case of discrete systems. So this is now what the symmetry test looks like, okay? This whole thing has to be 0. And notice that I got to this symmetry test, we arrived at this symmetry test without using the equations of motion. So that is the extra piece of information that we'll have to use now. Now we have to see what this symmetry test looks like when we use the equations of motion on it, okay? So now we're going to start using the equations of motion. All right, so now let's make explicit what this delta of the derivative of the fields is, okay? Because that's, what took us, all this derivation here. So now we need it. All right, so this 0 is the integral d4x over b4 of L derivative of delta x mu with respect to x mu plus d mu omega mu of eta and x plus derivative of L with respect to eta rho delta eta rho plus derivative of L with respect to eta rho comma alpha. And now I'm going to use the result that we obtained before, which is the derivative alpha of delta eta rho minus eta rho comma beta derivative of delta x beta with respect to x alpha plus derivative of L with respect to x mu delta x mu. Okay, so this is now I'm using the result. All right, now let us look at this term, precisely this term here, and let us compute derivative mu of the Lagrangian for reasons that you will see in a second. If I take this full derivative, total derivative with respect to x of this thing, chain rule says that this is going to be dl with respect to d eta rho comma mu of x, because I'm taking the derivative with respect to x mu, plus dl with respect to eta rho comma an index alpha, d mu of eta rho comma alpha, depends on x, plus the derivative of L respect to x mu. So you see, this term is inside this full derivative of L, sorry. This term here can be written, as the full derivative of the Lagrangian minus this minus that. So this is what we are going to do. We're going to write now this term, which is sitting here, as the full derivative of the Lagrangian minus this term minus that term. Okay? All right, so this is going to make the expression a little longer. 0 equals d4x over b4. And this is L d mu delta x mu. So that's why you have to start, writing less explicitly all the derivatives. Oops, this is an x. This is an x. Plus the derivative of L with respect to eta rho delta eta rho plus the derivative of L with respect to eta rho comma alpha, derivative alpha delta eta rho minus eta rho comma beta, derivative alpha delta x beta, okay? And now it comes the term that we just want to rewrite. So this dx mu times derivative mu of L, total derivative, minus the two terms, minus dl d eta rho eta rho comma mu minus dl d eta rho comma alpha d mu eta rho comma alpha. Okay. So, and this, I close the parenthesis. Okay, good. So now I'm going to start writing, putting things together as much as I can, okay? So let's see what we can put together. Well, we can put together a few things because, for instance, we see that this term and this term I can put together, okay? How? Well, like this. So I'm going to write it as 0 equals integral over b4 d for x, and I can write it as total derivative of the product of L times delta x mu, right? So this is the green term. This is this green term. You agree? If I take the derivative with respect to x mu of this, the derivative with respect to mu of L is here, and the derivative with respect to mu of delta x mu is here. And notice that here I can put the partial derivative because x mu only depends on x. There's no other chain rule says that this derivative on x delta x mu is the same as the partial derivative. There's nothing else. You agree?
Yes.
Okay.
Yes.
Now, let's keep on going. So now we have this second term. We just got rid of this 2 into this 1. So now this other term, d mu omega mu of eta and x, okay? And we keep on going, plus dl d eta rho, eta rho, delta eta rho, so that's this guy, plus derivative of L with respect to eta rho comma alpha, delta alpha delta eta rho minus eta rho comma beta, delta alpha delta derivative alpha delta x beta minus delta x mu. I absorb these two minus signs in here. Derivative of L with respect to eta rho comma mu plus derivative of L with respect to eta rho comma alpha d mu eta rho comma alpha. Okay, good. So now we're going to take this term and this term, and we're going to put it together. It's obvious, right? You know, it's the same. It's going to be the total derivative of this plus that. So that's one thing, okay? Then this term here, I need another color. So this term here, okay? And this term here, we are going to change by using the equations of motion, okay? So using the equations of motion, which is derivative of L with respect to eta rho equals total derivative, remember, because now we're considering a Lagrange which depends explicitly on x, respect to eta rho comma lambda. So we're going to use the equations of motion on these terms. Okay, so let's do that. So we have 0 equals integral d for x. And now we write the two blue pieces together, d mu L delta x mu plus omega mu. Okay? Now, first guy, this guy here, we write as delta eta rho, and then the derivative I can write as, using the equations of motion, as this. Right? So that's the first. So this was one of these guys. Okay? And then we keep on going. Plus And then we have the derivative of L with respect to eta rho comma alpha. This we're not going to change yet. Okay, minus eta rho comma beta derivative alpha delta x beta, okay, minus derivative, I'm sorry, delta x mu times, and this is eta rho comma mu, derivative lambda of the derivative of L with respect to eta rho comma lambda. Okay, so this is the second guy that we transformed thanks to the equations of motion. And then I have the last term here. The last term here, which is a plus because the minus sign I put out front, and this is dl with respect to d eta rho comma alpha, and this is d mu eta rho comma alpha. Okay, and if I'm not mistaken, I think that I put everything that there is. Okay. Any questions so far? I mean, one has to be careful and go step by step, but that's what I'm trying to do. Okay, but I think that it's just a question of being careful, and the rest of it is straightforward. I don't think it's very difficult. Any questions?
No questions.
Okay, so now I still have to group together several of these things. Okay, I have to group together several of these things. So in order to be able to do that, I'm going to start changing the names of some of the indices that I'm using. Okay, so here, for instance, here I'm using alpha and alpha, right? But these two indices are summed over. So in this term, I could just use any name I want. Instead of calling it alpha, I could call it lambda, and that's what I'm going to do. I'm going to call it lambda, okay? And the reason why I'm calling it lambda is because then I'm going to be able to put it together with other terms that have a lambda. Okay, so let's do that. So I think that at this point, this is the only thing I'm going to do. Okay, so let's write all the terms step by step. So 0 equals integral d4x over b4. Okay, and now we write the first guy, which is d mu L delta x mu plus omega mu. So this is the same. There's no difference, okay? There is no difference. Now, these two guys, let's see, I don't want to get lost. Yes. Now, this and that, I'm going to be able to write together. So that now I want to write together this guy and this guy. We're going to write together this and this together. So remember, these two guys. And this is why I call this thing lambda, so that I have the same index as here. Okay, so now I write it together. And it becomes derivative lambda of the product. So now let me write it down. And now we're going to make sure that this is true. Okay, so I'm writing it together. So this is the result of this new grouping of these two terms. Okay, so let's see whether this is true. Okay, so this is going to be the derivative of the Lagrangian times the variation of the field, derivative of the Lagrangian times the variation of the field, and then there is another one, which is the derivative of the Lagrangian times the derivative of the variation of the field. And that is this thing, derivative of the Lagrangian, derivative of the variation of the field. And the derivative of the variation of the field, okay, with the index lambda contracted, with the index lambda contracted, this derivative of the variation of the field is the same as the partial derivative, is the same as this partial derivative, because the field depends on x only, right? The field depends on x. So when I take the derivative on the field, this becomes the partial derivative. You guys agree?
Yes.
Yes.
Okay. Now, keep on going, right? So we just put these two together, but now I still have all the others. So all the others, I just write as they are. Okay, so it's minus derivative of L with respect to eta rho comma alpha, eta rho comma beta, derivative alpha delta x beta minus delta x mu, total derivative lambda, derivative of L with respect to eta rho comma lambda, eta rho comma mu, minus derivative L with respect to eta rho comma alpha, derivative mu, eta rho comma alpha, times delta x mu. These are all the terms. Okay, we are close to the end of the proof, okay? But we still have to do something, okay? So these are all the terms. Now, first thing that we do to make it, to really group together more all these terms is, again, we're going to change, the name of these indices. So this beta and this beta is going to become mu. So that's one change. And then another change is that this alpha and this alpha are going to become lambda. Maybe I should write it like this, lambda. So these two become a lambda. And the same thing here. So this guy and this guy are going to become lambda as well. Okay? I can freely, name them the way I want, so I want to do it like this. And the reason why I do that is because now this guy, this guy, and this guy, the three of them I'm going to be able to write into a single term. So that's the advantage of this thing. So d4x before, now this part is the same, d mu of L delta x mu, sorry, delta x mu plus omega mu plus d lambda of the dl with respect to eta rho comma lambda delta eta rho. Okay, and now the three terms are minus d lambda of, I'm going to write it up here, minus d lambda of three terms, the product of three terms, d eta rho comma lambda, eta rho comma mu, delta x mu, the three terms together. Okay, and now we have to see that I'm not cheating, that this is true, okay? That I take the derivative of this times that, and it gives me these three terms, okay? So let's see, for instance, let's see, the term in which I have the derivative acting on the derivative of L with respect to rho. So that guy, the derivative lambda acting on the derivative of L with respect to eta rho comma lambda is here. This is this guy. Is delta x mu eta times the derivative of L. Exactly. So this guy is here, the first guy. Then I have another one in which the derivative acts on eta itself. The derivative acts on eta itself. And this guy is here. Okay, because this guy, when I take the derivative on eta, what I have is eta rho and the derivative respect to mu and lambda, the two of them. Eta rho with the derivative of mu and lambda. And this is what I have here, eta rho with the derivative of mu and lambda, times delta x mu, times x mu. So this, when this derivative acts on this eta, gives me this term here. And finally, when the derivative acts on delta x mu, is this term here. Because then it's dl d eta rho comma lambda, eta rho comma mu, right? And then the derivative lambda of delta x mu, derivative lambda of delta x mu. So you see, that's why renaming the symbols, the indices, was useful in this case to recognize that these three terms can be written in a condensed way into this product of three terms. Okay, so let's, this is a little complicated here. So let's see whether you guys followed or not, or whether we have to do this thing more explicitly. So any questions or comments?
All clear.
Really? Okay, no questions or comments? Everybody could follow all these gymnastics with the indices?
Could you repeat the last one?
Who is which one is the last one?
The first term that is...
This first term here?
Yes, yes.
Okay, so this is when the derivative acts on delta x. So let's do it here and slowly, okay? So that means I have dl, d eta rho comma lambda, eta rho comma mu, and then I have d lambda delta x mu. Okay, so far?
Yes, okay.
Now, delta x mu depends on x only. Agreed?
Yes, yes.
So that means that this is the same as the partial derivative.
Okay.
And as you can see, it's exactly the same.
Okay.
Right? The index beta is actually mu. The index beta is actually mu, lambda and lambda, lambda and lambda. It's identically the same.
Okay, thank you.
Any other one? Who needs another one? Now is the time to ask. No one? Should I follow? Should I should I go on?
Yes.
Yes.
Okay. So now, we're going to write this thing in the following way. So we're going to write it as 0 equals, so we're still computing this 0, huh? Integral d for x, b4, okay, and this is d mu, and now L delta x mu plus omega mu, so I'm still writing the same, and now I'll do the last change. dl d eta rho comma lambda delta eta rho minus d lambda dl d eta rho comma lambda eta rho comma mu delta x mu. Okay, oops, this is like this. All right, so now, again, we'll relabel this index, and we're going to call it lambda. Okay, and we write this 0 as integral b4 d for x, and then this is going to be d lambda times derivative of L with respect to eta rho comma lambda delta eta rho plus omega lambda. So what I'm doing, I'm grouping together this guy with this guy into this guy, right? This is what I'm doing so far. Okay, plus, and then I have the derivative lambda of the rest. So that's going to be the derivative lambda of the rest. Who is the rest? The rest is delta lambda mu. So let me write it down, and then we'll check that is actually true what I'm saying. Delta lambda mu times L minus dl d eta rho comma lambda eta rho comma mu delta x mu, like this, okay? All right, and this whole thing needs another parenthesis. So I'm putting these two guys together, and this other term I put in here. So let's see that this term is this term here, okay? Now, if I take the derivative with a delta lambda mu, this thing, you know, suppresses the derivative except when lambda is mu. So this is going to be d mu L, but d mu L is what I find here. D mu times L delta x mu, and this is what I have, L times delta x mu. This delta x mu multiplies the L, and the derivative is the derivative of the two of them. Okay, so it is true that, you know, what, you know, is sitting here on top of the orange line is sitting here on top of the orange line. And then this extra term is here. 1, 2, 3, 1, 2, 3 terms under the derivative. Okay? We're almost there. Just one more step. Is this okay?
Yes.
So now notice that what I have is that 0 equals the integral over all space and time of the derivative d lambda of the whole thing. This d lambda, I could pull it out, and it's going to be d lambda of the whole thing. Okay? So that means that if this 0 is for any volume, then d lambda of derivative L with respect to eta rho comma lambda delta eta rho plus delta lambda mu L minus derivative of L with respect to eta rho comma lambda eta rho comma mu delta x mu plus omega mu, this whole thing, sorry, omega lambda, this whole thing has to be 0. So this now has become conservation, right? Because it says that d lambda j lambda equals 0, where j lambda is this whole thing in curly brackets, right? That I'm going to write again for its glory. Okay, so delta eta rho plus delta, sorry. I have to be consistent with the name of the index. Lambda, delta lambda nu L minus dl d eta rho comma lambda delta, no delta. Eta rho comma nu delta x nu plus omega lambda of eta and x. Okay, so let me check that I'm not screwing up any index here. So lambda is lambda, rho is rho, lambda nu is contracted, lambda is the same as that lambda, yes, and yes. Okay, so this, ladies and gentlemen, is Noether's theorem. right? It says that under general symmetry transformation, which has to be, close to the identity and continuous, right? It has to be a continuous transformation. Not discrete transformations are not allowed. Huh? It leads to this conservation. This conservation property is like a continuity equation for a super current. So this is like a super current. It's a current that has lots of things, okay? All right, so what we're going to see now is that we're going to see several. We're going to see how, this thing encompasses, right? It puts together lots of conservations that we all know. Like one of them is the conservation of electric charge, for instance. Doesn't look like it, but that's what it is. And another one is a conservation of all the other things that we already know also, like energy, linear momentum, angular momentum, also for fields, So this is Noether's theorem. Is the result of Noether's theorem. And as you can see, this is the reason why Emmy Noether got to be famous, right? Because this theorem is not that easy to obtain. So now we're going to see how this thing leads to a conservation. It's actually a conservation law, okay? And in order to see that, we don't need to see, the explicit expression for J. We just need to see that d lambda, J lambda, is the same as d0, J0 plus di, Ji, by definition, right? Because we are summing over 0, 1, 2, 3. So 0 and 1, 2, 3. Okay? So this, explicitly now, we're going to, spell it out. You're going to write out, all these things explicitly. D0 means derivative with respect to time. Now we remember what the zeroth component was of this, t and x column, okay? Plus, this is nothing but the divergence of J equals 0. So this equation is the same as this equation written in perhaps in a more familiar way. Now, let us integrate over three-dimensional volume, this whole thing. And then it's going to become derivative with respect to t of the integral over the three-dimensional volume, d3x of J0. And this is going to be minus, if I pull it to the right-hand side, d3x over the three-dimensional volume of the divergence of J. Okay? Now, the integral d3x of J0, I could call that a generalized charge, whatever it is. Maybe, I don't mean this thing to be electric charge. It could be whatever J0 is. When I integrate it, it's going to be the global charge of that, charge density J0, whatever it is. It could be energy density, it could be whatever it is. So that's a global object after I integrate over the density of it, okay? So this is, therefore, is the derivative with respect to t of that global charge equals this thing. But here I could use a famous theorem that I hope you guys remember, which is Gauss's theorem. Gauss's theorem says that this is the same as minus the integral over the surface, which is at the boundary of this three-dimensional volume of J times the surface, right? So that's the surface. So that means that the variation of this generalized charge is going to be minus the integral over the surface, which is at the boundary of this three-dimensional volume of J times the external differential, right? Remember that this is the vector which points, outwards of the surface. So what this means is that the variation of Q in time inside V3 equals the outgoing flux through the surface of V3. So you see it's a conservation, right? Q changes because what the variation in Q goes through the surface. It doesn't disappear. Q can only change because this change is going through the surface. Is through the surface, which is the boundary of the volume. So if Q diminishes, it's because the difference is going through the surface. And in particular, so that's a conservation, right? So that's a conservation law. For Q, whatever that is. Whatever it is, because it will be different things in different cases. In particular, if all the fields eta of x rho decay at infinity faster than r squared, where r is the radius at infinity, then derivative of q with respect to t is minus the integral over the boundary as before. So that's, of course, the same. But since s goes like r squared when r goes to infinity, right? Then if the fields decay at infinity faster than r squared, then this thing goes to 0 when r goes to infinity. So that means that, in this case, when the fields decay at infinity faster than r squared, then Q is actually conserved, doesn't change with time. Doesn't change with time. Then it's actually completely conserved, right? The variation in Q doesn't go through the surface because there is nothing through the surface, because at infinity the fields have already decayed. Okay, and then Q at T1 equals Q at T2 for all T1 and T2. Okay. All right. Now, questions at this point. So let me emphasize that this Noether's theorem is extremely important, okay? Extremely important. Now, what we're going to see, but I don't think we're going to see it now because today was already, hard work, okay? I mean, deriving this was, I think, hard work. So what we're going to see now, not now, the next day, is that this result of Noether's theorem for fields generalizes the discrete limit. So this result, or this Noether's theorem, Noether's theorem for fields generalizes the result for discrete systems that we had obtained before. And in order to do this thing, we have to do several things, right? We have to go from L, which is the Lagrangian density, to the true Lagrangian, which is the integral of the Lagrangian density. And we also have to do other changes, right? Because here we have fields, right? All these fields depend on X. And X is the special component X also, but it's also time. But in the discrete systems, we didn't have any X, we had time. Q depended Q dependent on time, but it's not dependent on any X, because for discrete systems, the X was replaced by a discrete index I that was going from 1 to n, right? So the fields eta rho have to become Qi, right? And other changes we'll have to make. Like for instance, delta x mu will have to become delta t, because x did not exist for discrete systems. It was only an index, a label I, but there was a t. So for the case when mu is 0, yes, this thing is true. So this is only for mu equals 0, okay? And delta eta rho will be delta Qi, okay? And other things, like for instance, what is delta, eta rho x? Well, this goes to nothing, because there was no Q with respect to x. The index x did not appear, okay? So this is nothing. And the derivative with respect to x, this also goes to nothing. Because for discrete systems, we did not take derivative with respect to I. Remember that x had to be I. And so doesn't exist for discrete systems. So this thing just we'll have to forget about it. So let's see if you guys do these replacements on this equation. Let's see what you guys obtain. Okay, let's see what you guys obtain. And this is something we will do the next day. All right, so any questions or comments?
No questions.
No questions? Okay, so then we're going to stop at this point, and I'll see you guys the next day. All right, so bye.